All right. Once again, hello everybody. Welcome to Quantum Computing PH 870. I'm having some issues with Zoom on my laptop, so just give me 1 second. So today, want to make sure, am I audible? Can you hear me?
Yes, sir.
Yes, sir.
Great. So today we are going to be looking at how to make a circuit corresponding to quantum teleportation and to superdense coding in the what do you call it, in the Jupyter notebook, which is the offline version. So in one of the previous videos, I've already shown you how to work with the Google Colab notebooks. So today we're going to do it with Jupyter notebooks, which will assume that you have an offline installation. And in the event that you don't know how to make an offline installation, the steps are very simple. You have to install the Anaconda Python distribution. Once you install the, okay, well, actually, you know what, I'll just show you how to do it. That's the best way, right? Okay. All right, so the first thing we want to do, I'll assume that you have installed Anaconda. Okay, you can Google and find out. For Windows, there is just a ordinary file that you have to download. Same thing for Linux and for Mac. So installing Anaconda should not be very difficult. So once you have installed it, there is one of the options in the configurations which automatically is used at the time of installation, you know, unless you say otherwise, and that is something called Conda Config. So what Conda Config does is it creates a base environment, and so for instance, you can see in my terminal window here, right? You can see this. There's a brackets base, right? So okay. Okay, please respond. Okay, yeah. So this is the command that we then want to use, conda env. Okay, so that creates a conda environment. Now environments are you know, separate rooms in which you can install software packages without one package, without the packages in one room interfering with those in another. Okay, so for instance, right now on my machine, I have installed, I have two environments. One is the base environment, default one, and the other is qiskit, right? And so the way that you would go around creating an environment is you would say something like this: conda create name, and then you would say something like qiskit2. Since I've already installed qiskit, I'll give it a different name, obviously. It will take a little bit of while. Once you have, so I'm aborting it because I don't want to go use that right now. Once you have installed this environment, now you want to activate it. Okay, so you use this command conda activate and then qiskit. So now you see what happens is that the qiskit, the environment has changed to qiskit, right? You can see that over here. Now what you want to do is you want to install, 1 second. You want to install qiskit in this environment, okay? So the command that you use for that is called pip. Pip as the Python package manager. You would just say pip install qiskit, okay? And this should install all the dependencies, etc., etc. Along with this, you would also want to install the Jupyter notebook. So that would mean install Jupyter. So you would say something like pip install qiskit Jupyter, right? So whatever is the list of package names, etc. Right? So I'm in this qiskit environment right now. When you are in this qiskit environment, then what you do is you let me kill this once. Okay. My laptop is an older version of a Lenovo Yoga laptop, so it's not exactly okay. So now once you have installed Jupyter, you would run it. First of all, it's very important to make sure that you are in the qiskit environment. Then you run, say, Jupyter notebook, and now if you just run it like this, what it will do is it will open up a notebook in your web browser. Okay, but since I've already opened up the notebooks, I don't want to open up another page. I give this command -- no - browser. Right, so then you basically get some links, and these links are to a web page which is running on your own computer, right? So this is a local server. Okay, now when I closed my Jupyter session earlier, what happened was that my kernel died. Kernel is not a rank in the armed forces. In this case, it is spelled like this: KERNEL, and it basically refers to, so it means core, or whatever is the central, as something which is central in the context of coding and computing. The kernel refers to the core program which is running your system, right? So you will often hear the Linux kernel or this kernel or that kernel. Okay, so now again, what I have done in this notebook, right? So what will happen when you open Jupyter is you'll see a directory listing which looks something like this, depending on which is the root directory in which you started the Jupyter server. So for instance, in my case, I have started the Jupyter server in this directory, which is, there's a tilde on cloud root code. Okay, and so if I look in this, you can see all these folders, and Jupyter will open up to a window which lists all these folders. Okay, so then you can make whatever folder structure you want. My particular folder structure happens to be something like this: IPython notebooks, teaching, and then qiskit tutorials, etc. And then there is a notebook which I have just made. So the way I made this notebook is that I went here and I said new. You can see on the right side, and then I said Python 3, right? And what it does is it opens up another browser window, which looks like this. Then when this browser window, you have a header cell where you can click and you can change the title, and I've set the title to something that is that will help me keep track of which file I was using. And then you might remember that in the session where I talked about using Google Colab, I showed you that there are two very nice things that you can do with these Jupyter notebooks. One is obviously, the coding part. There's one of the things is that you can type in Markdown format, so you can type LaTeX equations. And the second thing is that you can actually use these LaTeX custom commands. So I have a whole bunch of custom commands that I use in all my papers, etc. So for instance, you will see here, I have a command /browse/cat, which does what you expect it to do, /root, etc. Okay, and so this just shows me commands are just definitions, right? They don't do anything. Now, in order to run programs on the IBM quantum computer, what you need is an IBM account. Okay, and anybody can get an IBM account. Okay, so this is the IBM account I have, right? It's IBM Quantum, and I'm signed in. Obviously, you can see. Now, when you sign into IBM, what will happen is you'll see in this cell over here, you see API token, right? So API stands for Application Programming Interface. And you see this button here, you click it. When you click this button, what happens is this token is copied to the clipboard. Okay. And then what I have done here is that I have, so let me show you the sequence of commands, which is import Numpy, right? Numpy is for all the mathematical operations. From qiskit, import star. I've imported all the qiskit code, and I don't want to prefix every qiskit command with the name of the package. So I have used this expression rather than the first one. Then I have used this matplotlib inline, which is a shell magic, which will make my plots appear very nicely in the Jupyter notebook. Then in order to associate my notebook or my code with the IBM, with my IBM account, we have to use this from qiskit import IBM Q, right? So IBM Q stands for IBM Quantum, obviously. Then you say IBM Q dot save account, and in this you say IBM Q save account, and then you paste that really long string that you have just copied from your IBM account, and then you say IBM Q save account. Okay, and so what this does is, so I've already done that once. So what it does is it will create a file, a folder in your root directory, which is a hidden folder. So it starts with a dot. So it's .qiskit, and you see it has a single file, qiskit rc. If I look at the contents, it contains my token, a URL, and a verify is true, which means that it's been verified. Obviously, I will change the token after this session, but I mean, it's not like I have put any money in my IBM account, so it's not going to do you any good. Also, trying to read all the digits of this string from this recording is probably not going to be very easy or convenient for you to do. Okay, so now what we want to do is we want to make a quantum circuit, right, as before. Right? So we start with this. We say quantum circ is equal to quantum circuit 2, right? And then circ.draw, right? So right now there's nothing here. So it just shows the 2 qubits and an empty slot for the two classical where the two classical gates will go. So what we will do first is we will create the circuit which creates our bell pair, right? So by default, all of the input states to the circuits are initialized to the 0 state. Okay. Of course, the API has some functions which you can use to initialize it to some other state also, but by default they're all set to the 0 state. So the first step that we want to do is we want to create an entangled bell pair, right? And we want to create it in this state, right? And you can see here that I'm using Latex and so on and so forth. The only thing is that Jupyter notebooks, so you can see it has rendered nicely 1 by root 2, etc. I want to create this state. And the way I create this state is that I act with a Hadamard gate. So what I do is I say circ. Okay. My laptop's not responding. Let's not do that now. Okay. No, I don't want to close this page, obviously. Oof, man, this release is not too good, right? Let me try and close other tabs. Yeah, I'm waiting for the day when I can get the new MacBook Pros with the M1 chip, and I can say goodbye to the days of lagging performance. Yeah. Okay, so now what I want to do is I want to first add a Hadamard gate to one of the qubits, right? So I say circ.h, h is the Hadamard gate, and I specify the qubit number, right? So I add it to the Q1, right, which is this second qubit. Then what I do is I want to add a C0 gate. So the C0 is the controlled X gate, and I add it to the circuit like this, right? And then you say circ.draw, and you can see that I have added a Hadamard gate and this C0 gate, right? So what this will do is the Hadamard gate will take me, if I start, because from default I start with the 0 state, it will take me, let me write that down, root 2, 0, 1, and yeah, my global state will end up being looking like this. Okay, some error is there, get 0, 0, right arrow, root 2. Zero, zero, get 1. Okay, well, never mind. I'm not going to worry too much about it. So it becomes the state after the action of the C0 gate, you get the entangled state. Okay, you get this state 0, 0, 1, 1. All right. So what you can do is rather than typing in this set of instructions every time, you can make a function which creates a circuit for generating a bell state. Okay, so how do you make functions in Python? Let me show you that. You say def. Def is a keyword which says definition, function definition, and then you say bell circuit. Okay, and then it doesn't take any arguments, though we could give it an argument. For instance, if you want to specify which bell state to generate, so we'll say argument, and then we'll say something like state index. All right, and we'll just give it a default value for the time being. We'll set it to 0. And the way that now what we would do is we would create a quantum circuit. Okay, quantum circuit, and 2. Oops, sorry, didn't want to press Control Enter there. Then circ.h1, circ.cx10, and then return circ. Okay, so this is our bell state. So if you want, we can check that. We can call this function. I'm giving this a new variable name, circ2. So if I make circ2, now I can plot this. Let me plot it, and I get the same gate without I didn't put the classical registers in. I get the same state. Okay, now what Alice wants to do, if you remember, Alice wants to send 2 classical bits to Bob, and the way she sends them is by encoding them into her qubit. Okay, so she performs some operations. So for instance, if she wants to send a 0, 0, she doesn't do anything. If she wants to send 0, 1, she applies an X gate. If she wants to send 1, 0, she applies a Z gate. And if she wants to send 1, 1, she applies both the Z and X gates. Okay, so how do we do that? Let's say that we have the message. Okay, so we'll put the message in a string. Okay, and we'll just give it some value for now. Let's say 1, 0. All right, and now we will say the following. If Alice message, and so now, by the way, I have created a string variable in Python. Now I want to access the first element of the string variable. So I would use these square brackets, and I would say 0, because Python, all the indices, array indices start at 0. So I'd say if Alice message 0 is equal to 1, okay, and if you want to confirm, you can just do this here. So you see Alice message 0 displays 1, and Alice message 1 displays 0. Okay, so it's just showing me the output of the first character and the second character. So if this is the case, then what I want is I want to apply the X gate. Okay, so I apply this, and I apply it to which one is Alice's. Let's say Alice's is the first qubit, so I apply it to the 0 gate. Oops, if Alice message, and then I forgot to put a colon, and then otherwise if Alice message is 1 is sorry, if Alice message 0 is 1, then circ2 dot z acting on the 0. So what this does is, right, if message 0 is only if it is non-zero does it do something, and if you follow the logic in this in these two statements, you will see that if the message is 0, 1, it applies a Z gate. If it's 1, 0, it applies an X gate. And if it's 1, 1, it applies both the gates. Okay. So we can again draw our circuit and see what has happened. So we can see now that our circuit has an X gate that has been inserted in the first qubit, right? And that's because my message is 1, 0. Okay. So again, you can make a function definition. Okay. So you can say something like this, def encode message, and then we'll give it the following arguments. One argument is we'll tell it which circuit we're talking about. Then we'll say which qubit we want to refer to, and then the message. Okay. And what do we put in this in the code? Well, we put exactly what we had here with some slight modifications. Oops. Because now our message variable name is just message, and what we want to do is so one second. Yeah, small mistake I am making. Anyways, if message is equal to 1, then circ X and acting on whichever qubit I specify in the second argument, right? So I want to have that flexibility because I don't know whether it's Bob who's sending the message to Alice or whether it's Alice who's sending the message to Bob, right? So I want to be able to specify the qubit number on which this encoding acts, okay? And now the thing is that there should be another set of lines which does error correction, error checking. That means the user should not be able to send in some nonsensical message, but I'll leave that for later. Okay, so we have this bell circuit state and we have encode message. Okay, so let's just see how that works now. And we'll say again, circ is equal to bell circuit. Okay, so this will just initialize a circuit which creates the bell state. And then I'll say encode message. Then I'll specify circ as the circuit to which I want to do the encoding. Then I'll specify which qubit I want to, which is Alice's qubit. So Alice's qubit is going to be the 0, 1, and the message is whatever I want to specify. Let's say it's 1, 1. Okay. So I do this. Now let me just draw this circuit again and see what it looks like. So what it should look like is that you have the gate, Hadamard gate, a C0 gate. So this part generates your bell state. And since my message is 1, 1 and my qubit is 0, it has inserted an X gate and a Z gate. All right. Now, so at this point, the global state of the system is any one of the 4 bell states, right? And you remember there are 4 bell states, right? It's kind of difficult for me to but one second, I'll show you which ones those are. I have to share a different screen from a okay. Okay, so now these are the 4 states that I'm talking about. beta 000110 and 11, right? So the output of these of the circuit will depend on what my classical message is. So if it's 11, then what I want is I want the beta 11 state. So how do I get that? I get that by acting on my beta 00 state with an X gate and a Z gate. Okay. All right. So now I want to be able to decode this message also, right? So who wants to decode this message? It is Bob who wants to decode it, right? So Bob is in qubit 2. Okay. And this was the one part that I had been very sloppy about in the last class, which is that I had not really explained how this encoding process works. So let me do that now, and I'll need to go back again to my tablet. Okay. Because so what Bob wants to do, right? Bob wants to the protocol only works. Oops, sorry about that. There's an ant on my tablet. The protocol only is useful only if Bob can get the message in one shot with 100% accuracy. Otherwise, I mean, it's not really like you're not really doing anything useful. So let's see. So let me fill in those gaps right now to show you what Bob does in order to get his message. And before that, let me just give you another note about notation, because okay. Which is the following. We saw that there is a certain notation that is used in Nielsen and Chuang for these bell pairs. So let me just copy that. Okay, but this notation is not I mean, used universally, right? There is another notation that is used sometimes, which is the following. So you would refer to this beta 00 state as the following. We'd call it phi plus. We'd call this state phi minus, and similarly, this state would be psi plus and psi minus. Okay, so this is also alternate notation that is used. In fact, this notation is probably more common in the quantum computational literature. Okay, so what we have done, right, is we started with the message. Depending on the classical message, we applied a set of gates, and the global state of the system becomes one of these 4 options. It becomes phi plus, psi minus, or phi minus. Now we want to decode it, right? So what do we do? How do we decode it? So we have to apply. So we want that Bob should be able to perform a measurement right, and get the message that Alice wanted to encode, right? So let's say, for instance, that if the global state of the system is 5 plus, okay, so this corresponds to the message 00, right? So we want Bob to be able to measure 00, right? So that means what we want to do is the following. This is our state. We want to apply to this state some unitary such that the global state of the system ends up being 00. So now it's no longer in an entangled state. And at this point, Bob can make a measurement of both qubits without affect, because now both the qubits are unentangled. And so when Bob makes a measurement in the Z basis, Bob will get the result 0 and 0, right? And from that, he reads off, okay, that the message was 00. Similarly, let's say that if the message that Alice wanted to encode was 11, right? Then the global state of the system would be psi minus, which is 0110 by root 2. So again, we want a unitary which should take our state. And let me just make sure that I'm doing it the right way. Yeah, I'm fine. I want to take a unit. I want to take this state and I want to get the state 11. And so once I get the state 11 from this and I perform a measurement, what will Bob get? Bob will get 1 and 1. And from that, he will know right away that Alice wanted to send him the message 11. So the question is that, is there a unitary, right? We want this unitary and this unitary. We want all of these unitaries to be the same, right? So that's the question, right? Does there exist, question mark, does there exist a unitary which takes each one of these states, right? Which takes 5 plus to 00, 5 minus to 10, psi plus to 10, and psi minus to 1. And just for reference, let me use the Nielsen notation also, because that is psi plus is beta 00. That makes reading this, what's going on here, a little bit easier. This is beta is 10, right? And then this is beta 01. And beta 1. Okay. And there is such a unitary, and that unitary is actually just the inverse of the steps that are used to create the circuit to create this state in the first place, right? So let me just draw the state again. I have two qubits. One is with Alice, one is with Bob. Well, at this point, they're not with either one. Okay, so let me specify that these two qubits are not with Alice or with Bob. They're just out there somewhere with a third party. The third party creates a bell state starting with 00, right? So at this point, the state of the system is the following. Okay, and now we send the first qubit goes to Bob, and the second qubit goes to Alice, right? Now I just have a quick question for you all. Does it matter which qubit we send to Bob and which qubit we send to Alice? No, sir. Right. It doesn't make any difference because the global state of the system is going to be the same. And also, this state you can see is symmetric under interchange uh, of the values of the two qubits, right? Okay. So now the first qubit is with Bob, let's say, and the second qubit is with Alice. All right. And now the state of the system is this 5 plus or beta 00 state. That's the global state. Okay. In fact, so this is beta 00 or 5 plus. Now Alice wants to encode a message, right? And depending on what the message is, what Alice does is she applies an X gate and a Z gate, depending on whether the message contains. So this is if the first qubit, if the message she wants to send, so in the notation that I was using earlier, if message 0 is 1, then you apply the X qubit, and if message 1 is equal to 1, then you apply the Z qubit. So there is actually some circuit notation that you can use for this also. The way one would do that is that you have some classical bits here. You have lines representing classical bits, and then you put a control gate over here like this. Okay, so this is a classical control, and what it's saying is that if the first C bit is 1, if this C bit is equal to 1, then the X gate is applied, otherwise the Z gate is applied. And if not, then of course nothing happens. Right? Now at this point, what Alice does is she sends her qubit after she has applied both the both of these operations. Right? So this is the encoding process. This is the encoding. Before that, there was the preparation. And now Bob has to decode this message that he gets. Let me draw that again in a different. Right? So now this qubit goes off to Bob. Okay. Now both the qubits are with Bob. All right, but we'll keep the order of the lines the same. We don't want to mess that up. So what Bob does is he applies a C naught gate using Alice's qubit as the control and his qubit as the target. And then he applies a Hadamard gate. Okay. And now you will notice that this operation is precisely the inverse of the operation that is used in the state preparation. Right? So in the state preparation, you apply one Hadamard and then a C naught. And here also you apply a Hadamard and a C naught. Okay. And then what is Bob left with? Okay. So we have, 1 second. Always get confused which one is which one. Right. So this is Alice's qubit. the lower line, and this is Bob's cube. So if the global state of the system happens to be 5 plus. So what is that? 1 by root 2, 0, 0 plus 1, 1. All right. And now a C naught gate acts on this. Okay. And the convention being used here is the following, that the first qubit is the Alice one, and the second qubit is the one which belongs to Bob. All right, so if you apply the C naught gate using Alice's qubit as a control, then what happens to the state? So we're using the first qubit as a control, nothing happens to the first one, and the second one flips, right? So you get 1, 0. Now you see this state is no longer entangled. It can be written as 1 by root 2 okay, and I'll just put an A here for Alice multiplied by the 0 state for Bob. Right? So now what we want to do is we want to perform the inverse of the Hadamard gate, which is the Hadamard gate itself. So we apply the Hadamard gate to Alice. Right? What does that do? That takes this state and converts it back to 0. That's what we started with. Right? So we are left with 0 for Alice, 0 for Bob. Oops. For Bob and 0 for Alice. And Bob makes a measurement on both of these qubits, right? And so when Bob performs a measurement, what does Bob get? Bob gets 0, 0. So the message has been delivered. And you can show, and I'll leave it as an exercise for you, show the following, that if you start with the psi plus state, that is your encoded state. So what was psi plus? Corresponds to beta 0, 1. So you apply C naught and then H. You have to show that this gives you 0, 1. And then you have phi minus, which is beta 1, 0. Again, C naught plus H gives you 1, 0. And then psi minus, which is beta 1, 1. C naught plus H gives you 1, 1. Okay, so you should definitely work this out if you want to understand what's going on. Okay, so now having done all this, let's go back to constructing the circuit in Jupyter. All right, so let's see. And now I want to be a little bit careful. So I'm going to let's see, repeat this process, but with the knowledge now that the bottom qubit belongs to Alice and the top qubit belongs to Bob. Okay, so the encoding has to be done in the second qubit. And so I put encode message 1, whatever it is, 1, 1. All right, now I want to decode the message. So what does decode message do, qubit, one second. Decode message, well, it just applies it does the inverse of this operation, right? So it applies the controlled NOT gate using this. Well, I'll just leave this out for now. We'll forget about this. One can always customize it later on. So we'll say 1 0. So Alice's qubit is the control bit, Bob's is the target, and then circ H acting on 1. Okay. And then return circ. Right. So let's apply decode message to circ. And then, oh, what I want to do is let me do this again. I forgot to say circ is equal to this. Yeah. And then draw. Right. So we have the state preparation, we have the encoding and the decoding. Okay. And if you want, you can use it's a sort of a graphical utility. You can put something called a barrier. Okay, so what does this barrier do? Let's see. You see now there is this strip here, right? It doesn't do anything, right? It's just for show to separate the segments into different parts. That's all it's doing. Okay. And then we want another barrier, so we'll say circ.barrier. Okay, and then now I have two barriers showing the different sections of the circuit. All right. Now what we want to do is we want to measure all the qubits, right? Because what does Bob do at the end? Bob measures all the circuits, and he measures all the qubits, right? So circ.measure all, and once again circ.draw, and you can see that what it has done is inserted two measurement devices on the first two qubits, and now my circuit has automatically been expanded because each of these measurements will give me a single classical bit, right? So I started out, if you remember, with quantum circuit 2, but adding this measurement has automatically expanded my circuit so that it looks like what I would get if I had instead started out with the command quantum circuit 2.2. All right, so qiskit is pretty smart in that way. All right, so now what we want to do, let's visualize our let's see whether we get what we expect. So in this case, both of these measurements should give us 1 1, right? Now in order for qiskit to do this, right, what it does is it's a probabilistic measurement, right? So it's a simulation. So for the time being, what we will do is we will import, well, we've already imported everything, so we don't need to do anything else here. We just need to import from qiskit.visualization, import plot histogram. Okay. So now let's run this circuit. Okay. So we need to create a simulation, and to do that, qiskit has different backends. Okay. So the backend that we are using here is called AIR, AER. And so qiskit has named their backends after the 5 elements or the 4 elements, right? There is earth, water, fire, and wind, I believe, right? So this is earth, air, sorry, this is air meaning the wind, right? And then get dot, okay, let's, okay. And then you have to go through a bunch of formal commands, which, so what does this assemble do, right? Let's just quickly look at the help menu for assemble. Okay. It assembles a list of circuits or pulse schedules into an object. Okay. So basically what it's doing is it's taking all of these gates, right? And it's multiplying all of them and it's making one big matrix. Because the inside in the simulator, you don't want to apply each gate individually. You just, the whole thing becomes one big unitary gate. And now what we want to do is we want to use our simulator, right? So we have circ sim. This is our simulator, and we want to run our object. We want to pass it this object, okay? And then we'll get a result in this. So now our result object, let's take a look at it again. Help. It's a model for results, okay? And it contains a list. Well, we'll see what it contains. So let's say counts is equal to result dot get counts, and then circ. Okay, so what is in counts now? Now you see counts. So counts is giving me the value of this result object. Okay, and what is this? What are these values? Well, you see 1024. What does that mean? That means that this simulator, this air sim, it ran the circuit 1024 times. Okay, it ran the circuit 1024 times, and then after each run, it flipped a numerical coin, and depending on whether the result was heads or tails, it made the measurement, right? And you can see that the measurement, this is 1-1, right? That's what we expect to get, because that's what the message we have encoded, right? We have put an XZ here. So we expect to get, and you can also print it out, it will give you the same result. And now, if you plot a histogram, so what is a histogram? A histogram shows us which one of the outputs did we get. Since we only got the 1-1 output, or the histogram will just contain one big peak, right? So with probability 1. So this is the how you run a circuit in qiskit. I don't have time to show you how it works on a real quantum computer. We'll do that some other time for a different algorithm. Okay, and I will upload this notebook to Moodle so that you can access it. So when I upload it, it will be uploaded as a file which ends in extension .ipynb. That stands for IPython notebook. Okay. And so in order to use this notebook, you have to install Jupyter, etc. All right. I'm going to stop here and ask you if you have any questions. Any questions? Okay, I'll take that as a no. And I guess I'll stop it here because there is another seminar I have to attend at 6 o'clock. All right. So if you have questions, guys, please ask them on Telegram or Moodle or some other. Okay. All right. Sorry, I have to run off so quickly. Normally, I would stick around and answer questions. Can you hear me? Am I?
Thank you, sir.
Yes, sir.
Yes,
Yeah.
sir.
Okay.
Yes, sir.
I don't know. Maybe I'm just like talking into doing. Okay. All right, guys. See you on Monday. Okay.
Yes, sir.
Or
Okay.
maybe on Saturday, if you all agree to meet on Saturday, we can have a makeup class for tomorrow's for yesterday's missed session, or yeah, yesterday's missed session. Okay, is that okay? Can we meet on Saturday? I'll put the message on Telegram. Okay. All right. Bye bye.